you want to speak in French? No,
no, if if I were here for a few months, maybe I would be able to do that.
Bonjour à tous, nous avons donc le plaisir d'accueillir ce matin Andy Piacsek qui vient de Central Washington University et qu'on est plusieurs à avoir rencontré au labo par différents moyens. Donc il a travaillé, il était dans la même université que Brian Katz à Penn State. Il a travaillé sur le manque supersonique, donc il y a des relations avec François. Et puis, il s'est mis un petit peu à l'acoustique musicale maintenant depuis quelques années et travaille sur le violon. Et donc, on interagit maintenant aussi ensemble. Voilà, donc merci Andy.
Okay. Thank you, Claudia. I'm only staying here for a few weeks. I speak a little bit of French, but I don't think I'm quite confident enough to give my talk in French. If I could stay here for 6 months, perhaps by then I would be comfortable to do that. But so thank you for tolerating an English presentation. I also want to thank the D'Alembert Institute and Claudia for letting me come for 3 weeks. A year ago, I asked Claudia if I could work with her on a project in violin acoustics, because this is an area that is still somewhat new for me, and I wanted to learn from some of the experts in the field. So my talk today has 2 parts. I'm describing 2 different projects that I have with students at Central Washington University, and they're related because they both involve looking for very small changes in a system, things that are difficult to measure, which brings into account the uncertainty of the measurements that we are making. So I will talk in more detail about that process when it comes to measuring violins. So that is part 1. The second part, as you will see, involves measurements that we are doing with skull resonances to measure, to see if we can use that as a way of non-invasively monitoring the pressure inside your skull. This first part was done with my undergraduate student, Seth Lowry. Undergraduate, how does that translate in French? Baccalaureate? This is.
No, baccalaureate is high school.
Oh, okay.
Undergraduate is first year at university.
Yeah. Okay. So he graduated just this past May, and now he is in his first year of a doctoral program at the University of Texas. At my university, my program, I have only undergraduate students. I have no PhD students. So I am mostly teaching. I do some research, but I have to do a balance. So I will describe a little bit this playing-in project before I dive into the details of measuring uncertainty. So the goal, well, first of all, you might be familiar with a phenomenon that if you talk to performers, violin performers or cello or any stringed instrument, guitarists also, for the most part, have a strong belief that a brand new instrument does not sound as good as one that has been played for a while. You need to play it to, everyone has a little different way of describing what happens, but the effect is to improve the instrument just by playing the instrument. This is very difficult to measure. Some people have tried it in the past, but in my opinion, not as thoroughly as one could to make a definitive conclusion. So that was the goal of my experiment, just to see if I could measure something with violins. So we have 3 unplayed violins that are on loan. They're made by the same, they come from the same maker. They're made in China, but they have consecutive serial numbers, so they should be somewhat similar to each other. One of them will be a control. We don't vibrate it, we do nothing to it. The other 2 are stimulated. They are mechanically vibrated in different ways, and these are, well, one of them is a commercial product called the Tone Right. And if you haven't seen this already, I'll pass this around. This is the object. As you can see on the photograph, this just mounts on the bridge. Plug it into the wall. And this is just a transformer. This just vibrates at the alternating cycle frequency of your current. So here in France, it would be 50 hertz. In the US, it's 60 hertz. But you can get I'll just pass this around. You can get a little look at it. It's a very simple object, but this you can buy it online. These people make a lot of claims about how it improves your instruments. And even the person who loaned me these instruments believes that this does something. So there are many luthiers, many violin makers who also believe in this playing in process. So that was one of my methods. The other method was to take a mechanical shaker. I can put in any signal I want to that. And in both cases, I'm stimulating the bridge. I'm not directly vibrating the strings, but the bridge. The idea is just to put mechanical energy into the violin to simulate what happens to being played. And this is the signal that I'm putting in with the shaker. What I did there, I just took a movement of a Vivaldi violin concerto. I did a Fourier transform, and then I just did an inverse transform to make a 10-second recording that has all the frequency energy of the Vivaldi. Thought it doesn't. To be honest, I'm not sure how much it matters what specific frequencies I put into the violin, but I wanted to do more than just 50 hertz, so something a little more realistic. And then, so this is done continuously, so 24 hours a day, 7 days a week. And then once a week, approximately, we took all 3 violins into the measurement room and took 2 kinds of measurements that I'll describe in a moment, and then put them back into the shaking apparatus and continued to do that. So this took place starting in mid-April, all of May, and all of June, beginning of July, so almost 3 months of shaking. And then I'll talk a little bit. So to be honest, just, well, I've only had a very preliminary look at the data. Yesterday I was compiling some of the data for the first time, so you will have the opportunity to be the first to see some the preliminary results from this experiment. Oops. But first, I want to talk about the measurement process, because, like I said, my hypothesis is that if this shaking, if this playing in does anything, it's going to be a very subtle effect. And I was worried that this effect would not be observable within the uncertainty of actually doing this measurement. So I want to talk a little bit about how we do the measurements and how we determined quantitatively what our uncertainty is. This is what actually Seth spent most of his time doing when working with me, was coming up with the uncertainty quantification. So we take 2 kinds of measurements, and these are terms that are used in the violin research community. Acoustic radiativity, this is simply the pressure measured at some point, free field pressure. We do this in an anechoic chamber. The microphone is at 1 meter from the front of the instrument. And the source is a tap on the bridge with a hammer. I think I can point it out here. So there's the hammer. It swings on a little pendulum. And the hammer has a built-in force gauge. So we have a signal from the hammer, and we have a signal from the microphone. And radiativity is simply, in the frequency domain, the pressure divided by the force. We do something similar here, measuring the actual vibration of the instrument. So this is bridge admittance. And in this case, we're measuring, you could use an accelerometer, or in my case, I have a laser vibrometer, so I'm measuring velocity. And I'm doing it 2 different ways. The standard way, and I did it 2 different ways because it took me a while to learn the best way to do it. This is the laser dot trained on the opposite side of the bridge from where I'm tapping it. So it's the same hammer that I'm using here. And so I have a force signal from the hammer. It's now on the other side of the bridge. And I'm measuring the motion of the bridge on this side with the laser vibrometer. And the ratio of that velocity divided by the force is admittance. If it's measured there at the bridge, it's called the bridge admittance. Before I was measuring it this way, I was measuring the velocity of the plate just underneath the foot of the bridge on the same side where I'm tapping it. So those are two different methods. I'll call this direct and this one indirect. So the bridge admittance plot looks something like this. So it's a frequency response curve, and I'm only showing about up to 2,000 hertz, just so it doesn't look too crazy. But I'm plotting all three of those violins together, just so you can get a sense of how similar, but also how different they are. There are some, I won't go into the details now, but there are some specific signature modes. Those peaks correspond to specific vibrational modes of the top plate of the violin, but also of the whole corpus, of the whole body, twisting this way and that way. But I have another video, another slide a little bit later. I can show you those details, but I didn't want to spend too much time on that now. Okay, so let's talk about the repeatability of doing this measurement. So as you can see, I'm mounting the violin in what I'll call the rig. It's a place that has to support the violin, and we try to essentially simulate a free boundary by having very loose rubber bands supporting the violin on the bottom, and then also here at the top. So the violin is resting on a very compliant vibrational system. So there's a resonance frequency, but it's on the order of 10 hertz. So it's way below what I'm trying to measure. And but every time I take a measurement, I have to place it in there. I have to align the hammer to tap at just the right place. I have to align the vibrometer to aim at the right place. How sensitive is this alignment, or how sensitive is the measurement to doing this alignment? This is what I'm trying to find out. So here are the three violins measured using this direct bridge admittance. And I've measured them 8 times. So here are the details. So these are the labels of my 3 violins. These are the numbers that are actually written in, the model numbers that are written inside the violin. So consecutive model numbers, they must be similar. So I've measured each one of these 8 times, and I'm superimposing all 8 graphs on top of each other. So this one looks, I mean, you can start to see here that they're not identical, but they're quite close. Each one of those curves represents the average of 6 hammer taps. And after each violin was measured, I took it out of the rig, put it in its case. I put the next violin in there, did the measurement, took it out, put it in the case, took the third violin, did the measurement, and then repeated. So for each measurement, the violin was put back in. So I'm really trying to measure the repeatability of putting the violin back in. Now, these were all done on the same day, and I was, I had the same state of mind. I had a good memory of how I did it just a few minutes ago. So this is about as good as it gets in terms of repeatability, because I'm doing it very quickly. Even though I am taking it out and putting it back in, the repeatability, as we'll see, is not so good if I do this a day later and I put it back in, because my memory of exactly how I align things is a little bit different, and perhaps the environmental conditions, temperature and humidity, might be a little different on the next day. So variability on one day is fine. Variability when you're doing it one day after another is not so good. And then some modes have are more susceptible to this repeatability uncertainty than others. So if I zoom in on, see, which violin am I doing? I think it's 27. So I think I'm zooming in on these peaks here of that violin. So now you can see in a little more detail the variation of those 8 different measurements that I took. So the amplitude changes a bit. Sometimes the peak frequency changes a little bit. So looking at that, I want to explain to you how I calculate the uncertainty, the standard deviation. So I take all those measurements and I calculate an average at each frequency. So given the frequency resolution and the frequency band that I've chosen, I have 540 frequency points in that range that I'm showing there. And there are 8 measurements. So at each frequency, for example, this one here, I have 8 values, and I'm simply taking the average at that frequency, and I get that point. So the blue curve represents the average of all of my measurements. And visually, you can see the spread in my data. So I want to represent the spread, the height of that arrow, with a number. So a pretty standard formula for calculating standard deviation. So each of those measurements, I subtract the mean value from it. So that's the usual formula for standard deviation. And then I average that over the frequency range of interest. But that value still has units of admittance of what I'm measuring. So that would make it difficult to compare to, for example, the radiativity plot. So I need some way of normalizing it. So I just normalize it by the average value. So there's the average value of that whole band. So that's the average of all of these, of the blue curve. This is a logarithmic plot, so that's why it doesn't look like it's in the middle. And now when I take the ratio of this value divided by that value, I have a normalized standard deviation for that frequency range, and now I can compare that to, say, a different type of measurement like radiativity. And I can represent it, so the blue curve is still the average, and then the green curves are that average plus and minus the standard deviation. So now I have a wide curve representing, visually at least, the amount of uncertainty I have in my measurement. So now I can use this to compare the different measurement methods. So I have three. There's the direct bridge admittance. This is the one that gives me the best results. And for this frequency range, it's a bit different from the one I had before. It's wider. My normalized standard deviation is 0.066. If I compare that to the indirect method where I'm measuring the top plate under the bridge, it's quite a bit larger. And for a few reasons, but mainly it's very sensitive to the actual laser position on the plate. And then radiativity, where I'm using the microphone, it's somewhere in the middle, 0.085. So, but this one and this one are the two kind of standard measurements that people who do violin acoustics take. So I will be using those for our playing in experiment. Okay, so I wanted to explore, and I'll go through this somewhat quickly because I've got more interesting things to talk about, but I just wanted to show you what affects this, what causes this uncertainty. The precision with which you align the violin and the rig, I can think off the top of my head of maybe 10 to 20 different parameters, things that I should pay attention to. So I tested a few of them that I thought would be obvious, and that is the precise location with which the hammer hits the bridge. So I measured, I think, about 7 different locations, starting at the very tip of the bridge and then working inwards. And not surprisingly, if you just think about the physics of applying force to a bridge, and the bridge does this rocking motion, and it transfers the force to the top plate with those feet. And of course, there's also a sound post in the violin that is very close to one of the feet. So it's really a rocking motion that the bridge does to transfer that energy. So there's a torque involved, and as I move my hammer closer or away from the top of the bridge, for a given force, the torque is smaller. So I'm putting in less energy or less force to the violin itself. And you can see that with the amplitude. So as I move farther in, the amplitude decreases throughout. But otherwise, the shape is very much the same. And if I wanted to calculate the variability of that, I get a value of 0.08, which is less than that uncertainty due to measuring it with the indirect method. But it's more than the uncertainty of measuring it with the direct method. So this is significant if I measure it this way. This is not significant if I measure it the other way. So this is an important one. So from one day to the next, the humidity in your environment may be different. When I started doing these measurements, it was wintertime. In my lab, it was very consistently dry, about 25 to 30%. It's very dry in Central Washington University in the winter. So I was wondering what happens, if the humidity is higher and the violin absorbs moisture, how would that affect the measurement? So I put it into a controlled environment. There's a laboratory next door to me for sports athletic research. They put people into this chamber, and they can change the humidity, the temperature, the ambient pressure, and they look at the performance of somebody. They put them on a bicycle and see how well they can do if the humidity changes. I just put my violin in there and let it sit at 90%, 95% for over a day. So it really soaked up a lot of moisture. Then I brought it back to my lab and let it dry out. So it just, the water evaporated from the violin. But every hour or so, I would measure the mass of the violin, so I knew how much moisture content it had lost. Then I would do a test. And then an hour later, I would measure the mass again and do a test. So I had many measurements. I'm only showing just a few where the difference in mass is approximately 2 grams each time. And just notice that the color scheme is that the red curve is when it has the most moisture. It is the heaviest. And then after, this represents maybe almost 2 days later, it's lost 12 grams of moisture content from the wood. So it's quite a bit lighter. And consistently, as you go from red to blue, the curves shift to the right, which is what you would expect for a simple mass spring system. As it gets lighter, the resonances shift a little higher. Some peaks shift more than others. I mean, it's very clear here. This peak here, this represents almost like a Helmholtz resonance mode of the violin. This one is not affected as much. The plate motion is also involved, but it's these other modes that are measured a lot. Okay, so that's a significant variation, way more than the uncertainty of my measurement, at least throughout that whole range. So my question was, how much mass would the violin have to gain or lose before it became noticeable with my uncertainty? And so now I'm just taking 3 of those measurements from the previous slide. They are the black curves, and I'm superimposing them on a different day when I took 8 measurements and did a standard deviation. So that represents that's the blue curve here. So the width of that represents the uncertainty of my doing the measurements. But I did it the indirect method way. So this one has the bigger uncertainty. And so just visually, you can see that on the day that I did the uncertainty measurements, this was the mass of the violin, which is somewhere in between these two. So these 2 curves are very close to or within the spread of the uncertainty, but this one is outside of it consistently. So not everywhere, but in general, the conclusion is that for that measurement method, I don't really notice a gain or a loss of 1 gram in my violin, but more than that would be significant. So that is something one really needs to pay attention to when measuring the violin day after day, is what is the humidity and how much moisture has it taken in? So I always measure the mass of the violin before I take a measurement. And I did some other tests, like what if I forget to tune the strings? How important is that? Turns out not very much. And, oops, wrong direction. So this kind of wraps up my discussion of measurement uncertainty for violins. Just we developed a quantitative way of measuring how much uncertainty there is. If you take a baseline set of measurements with a violin before you start to do an experiment, just to measure how much uncertainty do you have with your measurement method. And obviously that variability is due to what you could call systematic and random errors. Random really are the errors that you just don't have any control over, or the things you don't know about. Systematic are the things you do know about. You could reduce those if you're aware of them, like making sure the hammer is always tapping the same place, or making sure the humidity is always the same. So both of those contribute to changes in the measurement. And yeah, these systematic errors like moisture content, string tension, and hammer, they become random if you're just not accounting for them. So the importance of doing this for us was that we knew that if we measured our violin repeatedly before starting the playing in experiment, we could establish a baseline uncertainty. How thick is the spread of my measurement data, so that when I start shaking the violin and I want to look for changes, the changes need to be larger than outside the uncertainty. Okay, so here are the results, hot off the press, because I just created these last night. The yellow with the dotted boundaries represent the baseline uncertainty using the direct bridge admittance. So this is our best way of doing it. Measured when the mass of the violin was 420.7 grams. And this was violin number 25. Then over the course of the experiment, now both Seth and I took measurements, and so we would take different weeks, we would trade off. Some weeks he took the measurement, some weeks I took the measurement. And as we discovered at the Via Favard workshop, that adds another layer of randomness, is who's doing the measurement, because two people may have very different ways of setting up the violin. They may be consistent with themselves, but they may not be consistent with another person. So for the purposes of analyzing this data, I wanted to be consistent with who is taking the measurement. So these are only the ones that I took. There's still some more measurements that Seth took as well. So sometimes they're 1 week apart, sometimes they're more than 1 week apart. And like I said, I always measure the mass of the violin before measuring it. So I have to include that because I know that plays an important role. And there's a lot to look at here, but there's really one important, the most important thing, and perhaps you can see it. If you compare the masses of all the violins, on the day that I took the baseline uncertainty measurements, the mass was 420.7. And you might notice that is by far the smallest mass of all the other measurements that I took. And from the previous curve that I showed, you might expect that would be the furthest to the right. All the peaks would be shifted to the right. And that is what we're seeing here. So it would be, if one were not paying attention to the humidity and the changes in the mass of the violin, and you looked at this, it would be tempting to say, oh, shaking the violin is causing all of these, I'm doing something to the violin, I'm lowering the resonance frequencies. But once you take into account the mass of the violin due to humidity, that effect pretty much disappears, because it's hard to see it in this graph, but there's no real trend of with time. So the more I'm shaking it, the more something is happening. I don't see that here. It's really swamped out by the mass. So this is one violin. I'm wondering if I should tell you which is which. So I'm going to show you three of these plots, or three violins. I haven't told you yet which one was the control violin. Let's see if you can spot the control violin in the three plots. So this is one of them. Here's another. And there's the third. Any thoughts about which one was the control violin? No. It's this one. Yeah, and it's, yeah, I mean, potentially, when I looked at this, I thought, well, there's a little bit less of a shift with this one than with the others, so maybe something's going on, but this will require a lot more careful analysis. Another way to look at this, and perhaps more relevant to what we perceive with the violins, I mean, obviously the shape of this curve contributes to the timbre, the tone that one particular violin has. And the reason one violin might sound different from another violin can be represented quantitatively with this sort of a plot. But it's hard to identify which specific peaks contribute to what we hear. This is exactly the kind of experiment, the kind of experiments that Claudia is good at, doing listening tests to see what we can actually discern. But one thing that does maybe use a little more reliable correlation with what we hear is to simply just do a band average and look at the levels. So the next plot is that. So this is 27. That's the control violin. So I have a band from 250 to 500 hertz. From 500, these are all octave bands. So 500 to 1,000, 1 to 2,000, 2 to 4, and 4 to 8,000. And the uncertainty is represented by the yellow band again. And then the individual measurements are represented with the colored curves. Some lie right within, some are a little bit out, but some are above, some are below. There is no pattern here associated with the amount of shaking that it had. So that variability can be explained purely from the, it's actually hard to say what that variability is due to, because the moisture content shifts the peaks in frequency a little bit left and right. It's not clear whether you get a change in the band averaged levels due to the moisture content. So that's going to require a little more analysis. Like I said, I just made these yesterday, so you're getting a look at them at the same time I am. I welcome your comments on this. So this is, so that was the control, and that seemed to have the most variability. This is due to playing in, and most of these are within the yellow band. And this is the one that was shaken with the tone right, and they're all inside the yellow band. So the preliminary conclusion is that shaking these instruments did not produce any measurable change in the violin, at least not analyzing it this way. Okay, so I just want to, that's part one, and I need to, well, I'll just mention that, I want to thank the people who loaned me the violin, and some people who supported our work in the lab. I don't know how much time I want to spend doing this one, because we got a little bit of a late start, but I can maybe go through this quickly just so you get a sense of what the other project is like, but I'm not going to go through all the details. So this other project does not involve musical instruments, but it does involve resonances. And the idea for doing this was provided to me by a good friend of mine who was a neurosurgeon, who told me kind of in an offhand way, because he knew I studied acoustics, that he thought when he does surgery on people, that patients who had elevated intracranial pressure, this is the pressure inside of your skull, if the pressure was high and he's tapping on the skull, he thought he could hear the difference just by listening. I was very skeptical that he could actually hear it, but I thought, well, this is an interesting problem. I could model this, and I could do some experiments to see if it is measurable. Whether or not you can hear it is another matter, but if we can measure it, that would be really useful, because right now the only reliable way to measure the intracranial pressure is to drill a hole in your head, insert a sensor to measure the actual pressure. And then the hole is also useful because if you have some head trauma, you fell off your bicycle, you were not wearing a helmet, you go to the emergency room, the chances are that the doctor will want to drill that hole in your head to relieve any pressure that builds up anyway. But there are times when you want to just monitor that pressure without drilling the hole. For example, astronauts who spend a lot of time on the space station, people in a long-term weightless environment, have symptoms of elevated intracranial pressure. They have blurry vision, they have headaches. So we would like to monitor that intracranial pressure, but of course we don't want to drill a hole in the head of the astronauts when they're on the space station. So this could be a useful technique if we get it to work. Some people have looked at this before, but nothing. So yeah, this is the standard approach where you insert sensors inside a skull. Something similar happens with eyeballs. So when the pressure inside your eye, the intraocular pressure increases, people have noticed changes in resonance frequencies of the eyeball, and these are the different mode shapes. But this is fairly predictable because the eye is surrounded by this membrane, and when the pressure increases, it's like stretching a drum head. When you tune a timpani drum, and put more tension on the drum head, the frequencies go up. Something similar is happening here with the eyeball. But the skull is not a membrane. It's a solid shell. And so the physics of what causes the frequencies to the natural frequencies of a spherical solid shell or a thin shell are different from a membrane. So this is what we were investigating. Oh, but we are looking for a similar effect. So these are basically the same kind of frequency response curve for an eyeball at different internal pressures. And they're showing how these, especially this one here, notice how this shifts higher in frequency as the pressure increases. So this kind of a plot is similar to what we were looking for. But we started with, this is some other previous experiments. We just, again, want to see if we can measure the relationship between the frequency response of a human scale, thin shell, but something with a very simple geometry. So we have an aluminum sphere that's thin that we can fill with water and change the pressure of the water inside, and see if we can actually measure changes in the resonance frequency. And we could, but we had to really pump up the pressure a lot because we wanted to make sure that we could see it. So these were unrealistically large pressures. I mean, way more than your skull has, about the pressure that's in your bicycle tire. So then phase 2 was, could we still measure that for much smaller pressures? And then this is where I'm at now. So in this year that I'm on sabbatical, I want to make progress on both of these projects I'm telling you about. And my goal with this project is to apply our methods to an actual animal skull, maybe a human skull, to see if we can repeat our measurements that we did with the aluminum shell. So there's our aluminum shell. We put accelerometers to measure the vibration. We excite it in different ways. Now lately we've been using a hammer, similar to what we do with the violin. So we have force hammer. This is the response with the accelerometer. The ratio, again, is the reliable measurement, which you could call this is the inverse of impedance. And these are two different accelerometer signals, but very clear resonance peaks. You know, it's metal, it's very low damping, so very sharp peak. So just like tap a wine glass, you can hear it ring. If you tap that metal shell, it really rings. You can actually hear those peaks. Tap your skull, you just get a thud. So much more damping. It's more difficult to do it with a human skull. But with a laser vibrometer, we measured the mode shapes of these different peaks, just to see if we can correlate the behavior of these peaks when we change the pressure with what the modes themselves are doing. And I'll point out that the simplest mode, what we call the breathing mode, where the entire diameter of the shell increases and decreases, you might think that would be the lowest frequency because it's so simple. But in fact, because you're really changing the stress and strain on the shell, that's a much higher frequency. So that's this one here. That's the breathing mode. This one is more like taking if you have a soft ball and you squish it that way and then stretch it that way, like a rugby ball and then a disc. That's the lowest frequency. Okay, so what we found really that was interesting is that for some of those peaks, some of those modes, changing the pressure has almost no effect. So these are the different, I'm sorry, the English unit, 0 psi to 100 psi, pounds per square inch. I'm not sure what that is in a useful metric measurement. I meant to write down the conversion, but I forgot. But 100 pounds per square inch is what you put into your bicycle tire. That gives you a sense of how much pressure that is. These did not change. But for this mode, and this one was at, where's the frequency? This is at about 9,000 hertz, so 9 kilohertz. A very distinct and regular change in the peak. So starting at 0 pounds per square inch to 100 pounds per square inch, it's almost linear, almost exactly linear. And we saw that with other peaks as well. But that rate of the change in the frequency with the pressure, that slope, as it were, is different for different modes. So we're still trying to understand why some modes exhibit more of a shift than others, and some have a negative shift. So this one went the other direction when we increased the pressure. So this, knowing that different peaks, different modes have different rates, could be used as a way to analyze the data that has a lot of noise. We have a small signal-to-noise ratio. Looking for patterns like that may be an advantage. When we did it, when we repeated the experiment at very small pressures, we still noticed the same shift. So here I'm just plotting the peak frequency as a function of pressure. And now this is, each of these tick marks corresponds to 10 millimeters of mercury. So that's more like a human skull-sized change in pressure. And then we also did a computer model in COMSOL. There's the shell is the red thing, there's water inside. We have air and an absorbing layer outside. We have a point pressure source. This was mimicking one of our early ways of stimulating it. So instead of tapping on it, we had a little loudspeaker underneath the speaker. So that's what this is mimicking. And what was interesting is that we observed the same shift. I mean, very similar. So that model does not exactly model our sphere because it doesn't have the valve on it. It's just a simple, perfect sphere. But the magnitude of the frequency shift at different modes was very similar to what we measured in the lab. And to help us understand physically what's causing this, we tried, I'm jumping ahead. So yeah, we have different slopes at different frequencies, just like we saw in the lab. But in a finite element program like COMSOL, you have an option to include something called geometric nonlinearity, which is a nonlinear relationship between strain and displacement, which happens for a curved thin shell. In COMSOL, you can just turn that off. Like, I don't want to include that. If we turn it off, then no shift happens. So this is, the dotted line is at 0 psi. The red is at 100 psi, and it just overlays exactly on top. So changing the pressure does nothing if you don't include that physical effect. But if you do include the effect, you see the shift. So this is how a skull is different from a membrane. You have to have this geometric nonlinearity to see this shift. And then for very small pressures, we see the same shift. And now, nice thing about having a model is that you can do all kinds of things with the material. I could just replace aluminum with bone. And as I've learned by talking with people who do biomedical acoustics, you can't simply say bone. You have to be more precise about what type of bone. You know, there's the porous kind of bone, there's the more solid kind of bone. I wasn't paying attention to that when I first put this in the model. I just looked it up somewhere. But the nice thing is that, yeah, I can change the material properties and run the model again. And again, I see the same shifts. You know, starting here and then going up to here. These are small pressures. And the rate of the shift is even larger than it was for aluminum, which is encouraging. So that's kind of what we've done so far. Our next effort, I had a student try to apply this to a sheep's head using the hammer tap, but the damping was so large we were not getting good enough signals. So I'm going to be, when I go back to Central Washington University, I will work with a colleague who has a cadaver lab, so dead bodies. And he's letting me do this experiment with the head there, and I will have to work out a procedure to change the pressure and also measure the pressure inside. It's complicated because, you know, they preserve these bodies, so the tissue inside the skull has now been almost plasticized by the fluids that they use to preserve the body. So that may affect my results, but mainly I'm interested in the bone and how it behaves, so it might still be useful. And I think that's pretty much what I wanted to show you. So thank you very much for your attention, and happy to answer any questions you have. on either the violins or the skulls.
Thank you, Andy. Are there any questions?
Francois?
For the violin, have you investigated the effect of temperature?
Only inadvertently. So this summer, so the short answer is no, not yet. Temperature. I think there is some, but I have not investigated it systematically yet. But I noticed it this summer when I was trying to repeat the humidity measurement that I showed you before. That was done with a different violin. I wanted to do it for my 3 test violins for the playing in experiment. So I did the same thing. I put them in the chamber, brought them back to my lab. But now it was summertime instead of winter. And in the summer, because of the way our building does air conditioning, it uses evaporative cooling. So the humidity was very high inside of my building. And so it wouldn't go below 50%. So I couldn't get the full range of masses for my violin, which is very frustrating. To overcome that, I took my violins outside. During the summer, it's maybe 35 degrees Celsius outside, to let them maybe dry out a little more than in my lab. But in the process, they warmed up. And I noticed some changes that were not consistent with just simply the humidity and the mass of the violin. So that anecdotal evidence suggests that, yeah, temperature does have an effect, but I have not investigated it in a systematic way yet. It's a good question.
Thanks. I have a question on the continuous vibration of your violins. Did you also tune them periodically during this time? Were you vibrating?
Every time I took them out to do a measurement, I put them on the scale to measure the mass, and then I also tune them to make sure.
So you tune them every time you do an experiment?
Every time I did a measurement, I tuned them. And I can just tell you that the tuning would only go off just a very small amount.
Okay.
Less than the amount that I tested, actually. Somewhere, yeah, I showed. I didn't spend very much time on. Oh, this one. Yeah, so here I deliberately detuned every string by that amount, so up to 3 semitones in both directions, and the amount of variability was quite small. So the amount of detuning I observed during the course of my experiment was less than that. But yeah, that is something to pay attention to.
I had a question on the bone experiment. So,
okay.
Bones are anisotropic.
Yes.
So is it something you took into account in your FEM model?
No. So most of my experiment really just used the aluminum shell. When we put bone into this model, I just looked up some properties of bone. This is before I really understood more about the different types of bone and anisotropy. So that was not included in this model. It would be interesting to see if that has an effect on the shift of the frequencies. I'm not interested so much in what the exact frequencies are. I just want to see how much they shift when you increase the pressure. If anisotropy affects how they shift, then that will be important. But
and also, probably there are lots of defects and irregularities on.
Yeah, so every person's head is going to be different. What we cannot do is specify what the pressure inside the skull is based on the resonance frequencies. What I hope that we can do is specify how much the pressure is changing as we measure the frequency shifts. And that more experiments need to be done because of the variability of bone as to how much those frequency shifts vary from one person to the next. Yeah, but we still have to, right now, my main focus is, can we even do this measurement with enough precision to even see those shifts. Given how much damping there is, just is it technically feasible to take these kinds of measurements? I know I can do it for a metal ball, but doing it for an actual head is going to be more difficult. But if it can be done, then those kinds of questions will be very important. Like, yeah, do individual differences in the inhomogeneity of a skull change the rate at which the frequencies shift? We will need to investigate that, for sure.
I have a question about the playing in experiment.
Okay.
Because
I don't know.
before you actually showed the band averages, I would have said that the control violins was the one which has most differences. And so I'm wondering, I mean, I don't believe in the playing in, but still I'm wondering, maybe the fact that you don't play the violin makes something happening to the violin that's not happening when you actually shake it. So you see, you want to see whether playing it will actually change something, but maybe it's because you play that nothing changes, and when you don't play, something changes.
This is possible.
And because that's what would go with as well with what some players say, that like when they leave their violin in a box for a long time, you know, they need to put it back into shape or whatever they say, you know.
Oh.
And so,
yeah.
So I don't know. I don't think this is enough to show anything, but.
No.
Just changing the point of view, you know.
That's no. I'm glad you brought that up because it emphasizes the need to do two things. One, to analyze these changes in a little more detail than I've done yet, but also, as I mentioned to you before, I would like to create a detailed survey that we can provide to the community of players and violin makers at large to find out what people really think happens, because there's not complete agreement. No. Everyone has a slightly different approach. So with different ideas about what happens, we have different hypotheses to compare our data to. There's more to do here. I mean, I think I'm also skeptical, but I want to at least do the experiment well enough to just say, stop talking about this. Don't let people, waste their money on products like the Tonerite when nothing's going to happen. But
But if people go on holidays for 2 months and they want to have their violins back, maybe. Yeah. I don't know.
And of course, there's a lot of psychology involved with how players relate to their instruments, whether they think it sounds good or not, or how it plays. And I can't test that, at least not this way. But I just wanted to see, can I actually see a physical change in the response of the violin? The fact that I'm not seeing a change, or at least I don't think I'm seeing a change, doesn't mean that there isn't something important to the player that's happening. It's just that I can't see a physical change in the instrument itself. So
that is the way we measure it.
Yeah.
And just to give you an idea, because you may not know the frequencies of the violin, but the lowest frequency of the violin is about 200 hertz. And this Tonerite shaker is at 50 hertz. So that makes us even more dubious about how it could work while it's far. It's subsonic, as you call it.
Right.
Far from what a player would play.
It's not emulating what a player does, but it does provide just some kind of motion, some energy. Yeah.
Any more questions? No? Okay, thank you again.
Okay, thank you for attending.